going to see, actually, this is next level of a probability. Yes, whatever topics we have seen so far, it's next level. Why next level am I saying? Because there is a target of a theorem, very important theorem to be seen in probability. So before that, I would like to recall our concept. In previous sessions, I have already taught that to you. That suppose two or more objects are being selected, or we want to discuss the probability of two or more objects being selected together one by one successively, then we multiply their probability by the fundamental principle of multiplication. This was mentioned in a lecture when previously I was teaching you the use of combination in probability. Let me give you an example that it will be very much clear to all of you. Suppose 52 cards are given. 2 cards are selected at random. Then question is about find the probability that both cards selected are kings. Such a question was given. I remember both of the cards are kings. Given that the selection is done with replacement. Listen my words properly. This selection is done with replacement. Now be alert. By the way, I have said we need to select 2 cards, both kings. Obviously, we have to keep in our hands. We cannot give it back. But if it is mentioned that this selection is being done with replacement, means first card chosen will go back to the group. Careful. That is why when we want both cards to be king, then we think this way. Probability of first king. So there are 4 kings in all. So probability of first king is 4 upon 52. Now, as the first card has been given back in the group, so that is why a second card also, if it is king, we require. So this probability will remain 4 upon 52, no change. And what I say, using fundamental principle of multiplication, here, as they are working as a team, so every time we put a multiplication between them. So this was the condition with replacement. Now, what happens when I do without replacement? Obviously, if I want both cards to be king, without replacement, first will be 4 upon 52. But second probability when I opt in, first card already has gone. Without replacement means this is not going to the part of the group now. We have to keep it away from the group. So there will be the reduction in the number of king by 1. So 4 minus 1 will become 3. And in total also 52 minus 1, that comes 51. But do not forget, still we are asking for both together. That is why we need to use multiplication here. And what formula, what principle are we applying? This is the fundamental principle of multiplication. I every time speak about it, that whenever two or more jobs are being done in such a way that they are dependent on one another, they are working as a team, then the result of all these will be multiplied. Okay, now this time we are taking example of probability. That's why we are multiplying the probabilities. This principle was taught in chapter permutation combination. So there was the matter of counting. When we count, in that case we multiply them. Okay. By the way, let's come back to the point. Now, generally, if I say repeated results, that is KK, both things. Now, suppose I ask this question: the 2 cards are drawn. What is the probability that one card is ace and another is a king? Listen my words. One card is ace and another is a king. So obviously, how many aces are there? 4. So we can say 4 upon 52. I am solving which replacement? So this card, first card will be given back to the group. So second time what will happen? Now we are going to fresh start. That's why only total will be 52 and card king they will be 4 as it is 4 by 52. Meanings are different. Check. These look similar. Let us come back here. Everyone focus. Here, when same without replacement, same condition is done. AK. Then what happens? First card will be 4 by 52, but this has gone away from the group. So there will be the reduction in the number of total card. But as the second card is different category, king. So there will be no reduction in the number of kings. Kings will remain 4. What has been less by 1? It is ace now. Okay. So in place of 4 cards, as soon as we take first card ace, that becomes 3 now. Okay. By the way, second selection is of king. So we will write here 4, but total will be taken as 51. My dear students, if you have attended the previous lecture, I told you that whenever 2 selections or more selections they are different, then this matters. That sequence, what is the sequence? Every time other than AK, that is first card ace, second card king, we have one more option. First card king, second card ace. Okay, and both the probabilities are similar. That's why we multiply this by 2. Check. Same we find here, AK or KA. So we multiply by 2 because of one reason. Because AK, one option, other option is KA. So total number required or total probability required will be the twice of this probability. By the way, I have explained all this in previous session. It is just to recall, just to take a revision. Okay. And intentionally speaking here, now there are 2 cases. 2 cases are available. What? With replacement, without replacement. Where we use the combination. If I say something before that, I want to hear from my students. In which case we can apply combination and how? After discussion, I have to say, I think combination, keep in mind, write it as a note. Combination is applicable only in without replacement condition. Whenever you want to use that pattern of probability, finding the probability, we have to use combination in this condition only. Okay. Otherwise not. Not in without with replacement. Without replacement only deals with combination. Okay. Means here I said like here one card ace, other card king is needed. So we will simply write in form of combination. This can be written as 4C1. That is one ace out of 4 cards multiplied to 4C1. One card king out of 4 cards divided by 52C2. Now 2 cards out of total 52. Favorable divided by total. Same is here. When I am asking for repeated selection, king, both kings. Now selection source is same. It's a king only. So total are 4. We need 2 kings. So simply you write 4C2 divided by 52C2. But this is possible without replacement. Okay. A certain reason is there. That's why. By the way, my main intention today is to teach. Every time we can see when the results we are finding of 2 or more selections, then probabilities are being multiplied. Now listen, because all the topics are related to each other. So from the beginning to end, everything should be clear. Here we find that when two or more selections are being done either with replacement or without replacement, we put a multiplication sign between them. So the rule says that if it's not different from fundamental principle of multiplication, it's coming as it is, but in the context of probability now. Okay, we are relating this to probability. If A and B are two events, then obviously I have written A and B are two events. They occur individually, separately. Okay. Now A and B are two events. Then first, probability of A intersection B is equal to probability of A into probability of B. What is the meaning of A intersection B? Every time you should know whenever intersection we are using, it means both together. Okay, so probability of both together, both, try to understand, two kings, both kings, one ace, one king. So we want both selection of ace and selection of king, one ace, one king. Okay, both together. So for both we take the symbol intersection from set theory. So probability of A intersection B can be written as probability of A into probability of B. Now the question is, I have taken with replacement condition, I have taken without replacement condition. Here, how to identify that this product which we have taken denotes which condition, with replacement or without replacement? Focus. So for this we have a special arrangement, the different topic, that is the different way of writing. We see that whenever probability of A and probability of B I am writing, its a simple meaning is they are individual probabilities. Check 4 by 52, 4 by 52. They are not affecting each other. Okay. 4 by 52, 4 by 52. Simply I have written. First your doubts and comments. So, what is that spatial arrangement? It says that probability of A intersection B is equal to probability of A into probability of B by A. Now see, I have used a new symbol. Actually, this is speaking a lot. Different terms are coming up. Now let me tell you, by the way, either this first one or second one, whichever according to condition you apply, this is known as multiplication theorem of probability. Now you can see this topic we have taken as fundamental principle of multiplication. Here it is known as multiplication theorem of probability. But what is the difference between these two? This formula we apply whenever the condition is of with replacement. Listen my words one by one. Condition is of with replacement. This we apply when condition is of without replacement. Now I have not said anything about this type of symbol. Let me elaborate, let me explain. Here comes B by A, B slash A, or B on A. What does it say? This is known as probability B by A is known as conditional probability. It is known as conditional probability. It says that conditional probability of whom? Here we can see both events are involved. Every time this upper one. It's known as conditional probability of event B. Of event B if. Now what condition? Obviously, if I'm saying conditional probability, what is the condition? Condition is A has already occurred. If A has already occurred, obviously you are asking, for example, let me tell you, recently I gave conditional probability. Let's come back to the topic now. When two kings, actually this example suits too much. We can take other examples like a selection of balls, selection of some other items from a group. Okay, this is common. If you want, we can change it, no problem. Now let me discuss. As we can see, conditional probability is the part of without replacement situation. So we will discuss here that only. In without replacement case, you could see when two cards are being selected, we require both king. Event A means first card is a king. Event B means second card is a king. We need both kings. Two cards are selected. So what was the probability? 4 by 52 into 3 by 51. Now you can see very well why this 3 upon 51. Question is why 3 upon 51? Reason, because occurrence of the first event is affecting, influencing the second event occurrence directly. You can see first is a king, that's why. Here's the reduction in number of king and reduction in the total also. So that is why here in case of without replacement I have written probability B on A, or simply say conditional probability of B when A has already occurred. A has already occurred. Okay, so this symbolizes conditional probability of B. Here it says that we are finding probability of B when A has already occurred. Now it's a question mark. What about with replacement? We find that in case of with replacement, when we discuss the same condition, double K, first remains 4 by 52, second also remains 4 by 52. That means first event does not affect the second event. Occurrence of first event does not affect the second event. So probability remains as it is. You can see whatever probability of king was in the beginning, the same probability will be there in the second time also. So this case we have taken in first one. That is why I have written probability of B. Here I have not put any symbol like /A. Reason, because this is not being affected by the first one. There is no effect. So why to say that first has already occurred? Okay, occurred, but this remains as the normal probability. Generally we find there is no change in the probability. Okay, so what we have to do, whenever we apply multiplication theorem in such a way and we see that second event is not being affected by first one, then in such a case we say these two events are not related to each other, or there is no effect of one event over other. This gives you a new term known as independent events. Independent events. So you can write one more thing. Two events are said to be, let me actually write here. This will be repetition. That's why I was thinking to dictate. Two events A and B are said to be independent if probability of both events together is equal to probability of A into probability of B. Example. Let us consider, we will see here, let us consider there is a sample space, very well known sample space. When a coin is tossed, two times. Now, here I want to check two events defined. Event A, exactly one head. Check, exactly one head. Event B is exactly two tails. I want to check whether they are independent events or not. Yes, in this theory, it will help us out. So this example will support us to understand independent events in a better way. Now, I have taken event B. First of all, you see what is event A, what is event B. That is must to know. Now, if I ask for event A exactly one head, so see which result, which outcome belongs to A. So we can see A is equal to only HT and TH, exactly one head. B is exactly two tails. Now, if I want to write is correct now. Yeah. If I want to write A intersection B, we can see there is nothing in common in A intersection B. Yes, check. Nothing in common in A intersection A and B. So A intersection B is 5. So whenever A intersection B is 5, probability of A intersection B, this is 0 for sure. Okay, because nothing is common. Now, why am I looking for this probability? Because formula says if they are independent, then probability of A intersection B is equal to PA into PB. Let's see that. Probability of A intersection B is 0. Now, probability of A, if I want to find, so this comes out as 2 by 4. Simply as you find 2 by 4, the same way. Now, probability of B, that is 1 upon 4. Now, check whether the product of these two is equal to the probability of A intersection B. Obviously not, because clearly it's visible. Probability of A intersection B is 0, and the product of these two, 2 by 4 and 1 by 4, that will be apart from 0, any value, but that will be a non-zero value. So as we can see that probability of A intersection B is not equal to probability of A into probability of B. So these two events are not independent events. They are not independent events. Your doubts and comments now. Now, next topic for discussion is conditional probability. Recently, what I said. Actually, we have understood well conditional probability. Conditional probability. Now, this point is to be noted. Suppose I want to find, listen, suppose I want to find this probability directly. I don't want to discuss about here that what comes first. Simply, in some question, I want to find it out directly. So it's not means directly like impossible. We can shift this P of A, probability of A, to left hand side to make a formula for conditional probability. Probability B on A. I repeat, This is known as conditional probability of B when A has already occurred. Can be given by the formula probability A intersection B upon probability of A. Now this is very much clear that in denominator we are using probability of A. It says that A has already occurred. But suppose in some case I say conditional probability of B, this time it was B of A, when B has already occurred. What does it mean? This time A is depending on B. Now everything will be changed. How? We will write probability of A on B. Now this shows that B has already occurred and A is depending on B. So this will be written as probability A intersection B divided by probability of B. Now you can see in division we have taken probability of B because it has already occurred. But the question is why numerator is same. If you remember in set theory already we have seen that either it be A intersection B or B intersection A, they both are equal. Means commutative property. Okay, that is why we can take it B intersection A or A intersection B, doesn't matter. But its sense is probability of the selection of both. Okay, so this way you can see all these topics in dependent events, multiplication theorem of probability, conditional probability, they are related to each other. Okay, it depends on condition. We will now further think of about conditional probability more. Okay, let's see what is this about. But before that, I want to discuss multiplication theorem for events in number more than 2. So far we were discussing about the 2 events. I said when 2 events are there and they are independent. Listen, it's a very important statement. When 2 events are there, they are independent. So simply we write probability of their intersection as the product of their individual probabilities. Now this theory you can apply for more than 2 events also. Suppose 3 events are given and they are independent, so you can write continuously PA into PB into PC. Doesn't matter. Also, this should be discussed for conditional probability case, that is without replacement. If 3 events are there, then what happens? So we will copy down again the formula for 2 events. What was that? 2 events, they are dependent on one another, and obviously in simple language we can say that's the case. Which case? Without replacement. So probability of intersection can be written as probability of A into probability of B on A, conditional probability of B. Now suppose A and B and C, A, B, C are 3 events. Such that A occurs first, then B, and C at last. Then probability of A intersection B intersection C. What does it mean? No change. All three together. Like they were both together. Here, all three together. This can be written as, see the sequence, A first. So first probability will be normal. There is no change. As it is. Multiplied by second probability of B will be written as conditional probability. But that depends on A only. In multiplication, we write the probability of C by AB. C by AB, which says that here we are looking for the conditional probability of C when A and B already have occurred. By the way, this is a formula for 3. Okay. Now here, suppose I want to discuss. Obviously, it's nothing new, but still, let's take one example to understand it better. If there is a box, 5 black, 7 blue, and 3 red balls are there in the box. Here, if I define event A as a selection of red ball, B selection of black ball, C as blue ball. Listen my words very carefully. 3 balls are chosen at random from this box and without replacement. It's without replacement. Intentionally, I want to take the case of this conditional probability only. Without replacement, they are chosen. What is the probability? First question. What is the probability? All 3 are black. 3 balls are chosen. What is the probability? All 3 are black. Now, all 3 are black means if I consider A, B, C, here black ball is referred by B. So I want every time B. That is, I have to write this language as probability of B intersection B. Now this is taking without replacement. Listen my words repeatedly. I am saying. See, writing the formula is a different thing, but applying is apart from it. How? See, we will apply the same method of without replacement. What was that? I want first black. So what is the probability of black ball? 5 and 7, 12 and 3, 15. So first will be 5 upon 15 multiplied. Now as we know that it is the case of without replacement. So next I require black ball again. So there will be one reduction, means 4 upon 14 multiplied by, it's going on, one more reduced, 3 upon 13. So this is the result. You see, there is no use or discussion of formula here. It's a symbolic language only. We are using symbols only to say that the second is dependent on first, third is dependent on both, this much. Otherwise, by applying, we should get this way. We should understand this way. This much your doubts and comments. Now, this was the case in the same example when I want all the 3 balls to be black. Now, in a case where I want 2 red balls, 1 black. This in symbolic language can be written as R, B. Yes. I want 2 red balls, 1 black ball. What is the probability? That is all 3 together. So if I consider the same sequence R, B, so I find that this probability will be written as R intersection B. and going on the same selection without replacement. So probability of first red ball. The red ball here is 3 upon 15. We write here 3 upon 15. Now second red ball without replacement. So number of red ball 3. So this becomes 2 here upon 14 into. Now third ball is to be black. 5 upon remaining total 13. Check. Total is reducing. It's without replacement condition. Now, point to be noted, very important thing we have to discuss here. Everyone focus. RRB, that is 2 red, 1 black. In such a case, when these balls are different, we have to think of the sequence arrangements also. It can be RRB, it can be RBR, it can be BRR. Now to sort it out, we cannot take each differently, separately and solve it. That will become a long solution. Is there not any shortcut to understand? Obviously, we have used permutation combination. Now, it's if I consider RRB is a word, RRB is a word. A simple question: how many arrangements can be made of this word? Total 3 are there, so 3 factorial. Now repetitions are 2, so divided by 2 factorial. Finally, we get 3. That means to find the final probability in such a case, when we require 2 red, 1 black, multiply the result by 3. Why? Because we are finding for all RRB, RBR, BRR. All 3 are involved here. Okay. This way you will get the probability when their colors are different. Your doubts and comments now. Now, we have seen about conditional probability. Now, this was a case where we can see that one event is affecting other. Mainly, we discuss such cases. 2 events are there, one affects other. That's all, nothing else. Let us suppose a special case. I said in the beginning, actually, these topics are not different from each other. They are related. That's why, from the beginning to end, we have to understand each and every topic. This is the next step to conditional probability. What is that? Let us discuss. If A event is given, this is the single event, and now I will repeat my statement. Previously, I have taught a conditional probability case when one event is being affected by or related to exactly one other event. In this condition, A is related or being affected by E1, E2, E3, and this way, if I continue, total n events. A is point number 1. A is related to, this related can be written as depended on also. Depended on n events, even E2, En, such that first probability of EI is greater than 0 and obviously less than 1. Or I can say that each event exists. There is no event with probability 0. Careful, it's very important to know. There is no point of discussion that if one of the events is not existing or not defined or not such a case. All events are well defined. You can mention all events are well defined. existing. This is for your clarification. Further, next, let me tell you this I have written, do not get confused. EI represents all these elements. Okay. Now, n events are mutually exclusive and exhaustive. I hope you still remember. Mutually exclusive and exhaustive means they have nothing in common, no element is common, and their union will make the sample space. Even union E2, they all together make the sample space of a condition. Okay. Such is given. Okay. I am not going giving you differently like even EI intersection EJ. This is phi, nothing in common, and even union E2 union up to En. This makes the sample space. This way you can understand. This is exhaustive. This is exclusive. Now, what I want to say. I said that a individual is related to each one of them. Okay. In such a case, if I want to find probability of A when all these n events already have occurred, probability of event A when all n events have already occurred. Obviously, when we are writing this statement, when n events have already occurred and probability of A be required, so that is like something conditional probability of it. But when it was the case of only one event, so that was easy to write A/B. But here we are talking about n events already occurred. So that will be A/T1, E2, E3 up to En. By the way, how to write? Probability of A when all n events have already occurred is given by that will be the sum of all these probability A intersection even, A intersection E2 plus probability of A intersection En. Keep in mind, here probability of A is the sum of all these probability, where each probability has been taken as the probability of intersection between A with individual events, even E2, E3 up to En. Check. Because A is related to all, it's depending on all. Okay. This rule is known as law of total probability. This is known as law of total probability. But I know this theoretical pattern, if I write, very less chances are there that students have got it. That's why I'm not asking your doubts and comments. I will explain with example, then you will come to know. Now, honestly speaking, maximum time I have seen this one. Whenever students see this theory, they say it's a bit difficult. I don't know how many of you are thinking so. Now let's take example, and after that you raise your views. Let us suppose There are three boxes. Three boxes. Box 1, box 2, box 3. And each box has the same colors of balls. First one has 5 red, 7 black. Second box, it has 3 red, 9 black. Third one has 6 red, 6 black. By the way, intentionally I have taken this total number to be same in all. 7, 5, 9, 3, 6, 6. Okay. Intention is something else. Now you can see a different case. Here, suppose I want to find the probability. Like I am asking direct question. Find the probability of the selection of red ball. Try to understand the procedure. Find the probability of the selection of red ball. Now here comes a very big question mark. Red ball. But from what? Box 1, box 3. What is the change in this concept? In this concept, the change is previously, any time when there was a case of the selection of an object, then source was the same. Source was common, a single source. Be it the pack of 52 cards, you need to select 2 cards out of it. So 52 cards, there is one pack only. Be it the case of selection of balls. So far I have given the example of one box only. Be it the case of throwing the coin, it's coin. Being repeated, dice. But source is one. In this condition, you can see we have 3 boxes as sources. And red ball is available in all 3. 1, 2, 3. So when I'm asking red ball, first question comes from which box? That's the question. Here, by the way, I was explaining you this thing. Here we find I said A is an event related to all these individually, separately, 2 different events. So how can we compare this condition to this one condition example? Red ball is common in all the boxes. So selection of red ball is A. Selection of red ball. But red ball is related to boxes. So even event is selection of box 1. E2 event is a selection of box 2. E3 events is a selection of box 3. This way, I said A is related to even equity. This is the relation actually. That R is available in box 1, R is available in box 2, also in box 3. So when you select the red ball, so question is about the selection of these boxes also. My dear students, let me tell you, whenever, like it's not specified that something about selection of boxes, what is the probability of the selection? So we consider such a condition when nothing is provided about probability of this selection. We consider this to be equally likely. Equally likely in the sense there are 3 options for the selection, either from box 1 or from box 2 or from box 3. So equally likely means each probability will be 1 by 3. If n objects are there and the selection of their probability is equally likely, or simply all of them are equally likely, then each probability becomes 1 upon n. This theory are taken from 10th standard. Means if 4 boxes are there, if they are equally likely, nothing is mentioned. So we consider each probability to be 1 by 4. So here I have sorted out one thing, that what is the probability of each event. But why suddenly I started to discuss this probability of boxes selection formula? This says that probability of A using law of total probability has to be expressed as the sum of these probabilities. So in the given example, we will write probability of red ball. This will be probability of red ball intersection box 1, probability of red ball intersection box 2, probability of red ball intersection box 3. Now let me explain the meaning. This is most important part. When I say R intersection B1, its meaning is selection of red ball from box 1. R intersection B2 means selection of red ball from box 2. Here this is selection of red ball from box 3. That is the sense of writing intersection. Okay. Now, how to expand these? Remember, turn back your pages. You see again multiplication theorem. R intersection B1. Out of this, my equation, which event occurs first? Selection of red ball or selection of box 1? Obviously, in each case, box will be selected first. Now, using multiplication theorem, we can write this as probability of box 1 into probability of red ball from box 1. It is looking like conditional probability, I admit, but its meaning is red ball from box 1 plus probability of box 2 into probability of red ball from box 2. Multiplication theorem. In the case of conditional probability, probability of box 3 into probability of red ball from box 3. Now let me write this properly. As I have already said, probability of boxes, each selection will be 1 by 3. No problem. It's 1 by 3. Now clearly visible, red ball from box 1. This will be 5 upon 12 plus red ball from box 2. So that will be 3 upon 12. Let me write box 2 probability, which I have not written. Probability of box 2, this is 1 upon 3 into 3 upon 12 plus box 3, 1 by 3. From box 3, how many red are there? 6. So 6 upon 12. To find the probability of selection of red ball, we need to evaluate. So I see 1 by 3 is common. I can write probability of red ball 1 by 3 common. Inside the bracket I am left with 5 by 12 plus 3 upon 12 plus 6 upon 12. 5, 3, 8, 6. 14 upon 12 into 3. So this finally can be written as 14 upon 36. 2 7s are 2 18s are. Finally we get 7 upon 18. Check. That means the probability of selection of red ball in the given condition is 7 upon 12. Your doubts and comments. So we have discussed this law of total probability. For that, you must know the condition that a single event is dependent on n events, and given that all those n events occur together, occur first, then at last we think of the probability of that single event A. In the given example, you could see that. Now, there may be one additional condition. What happens if A has already occurred? In the same case, all the cases, all the conditions are same. But the question is, if A has already occurred and we need to find a probability of one of those n events, then what? It's a bit confusing. Again, let us see. If A event depends on n events. What were they? Even E2 up to En, such that same thing I will do, such that first one, that probability of each event is greater than 0. Second, they are, let me write, they are mutually exclusive and exhaustive. This clarification I have already given. Then, so far we were finding A by even, A by even. Check here. That formula was told you, total probability. I am asking now, what happens if A has already occurred and we require the probability of one of those events? So let us suppose EK denotes one that event. Then probability of EK, where EK denotes one event out of these 10 events. If A has already occurred, is A has already occurred, we need to find the probability of EK. This will be denoted as probability of EK by A. Check conditional probability of EK. Doesn't matter. A has already occurred. At this stage, we will apply the formula for conditional probability. Conditional probability. Turn back the pages again and check what is the formula. Probability of EK on A given by probability of A intersection EK upon probability of A. Be careful. We are discussing an important topic now. This is the conclusion of all the theories of probability seen so far. Probability of that particular event on A condition probability will be expanded by the formula, simple formula we have. But what does it mean? How is it used? We know that. See, A intersection EK, this is one of the terms in the total probability only. Obviously, this probability of A, see the previous topic, total probability. How we write? Probability of A, this will be A intersection even plus probability of A intersection E2. And for sure, when EK is one of these, so we have one of the terms like probability of A intersection EK also. So this formula indicates that clearly we need to pick one of the terms favorable and we have to make it numerator. Means this can be expanded as probability of EK into probability of A by EK divided by probability of A. This is known as Bayes theorem. This theorem I was talking about in the beginning. Bayes theorem. Bayes theorem is actually the conditional probability of one event out of these n events when the dependent event A has already occurred. That is Bayes theorem. But how to use that in application? This may look a bit complicated, but I promise when it comes in application, this is nothing difficult. I will explain using the same example. This much is still your doubts and comments. Now I say the same example we will take previously. Do not forget what was given. In the given condition, 3 boxes, we had to find the probability of red box, selection of red box. So simply we apply total probability formula. Now if I say in the same example, if I say that these 3 boxes are given, with the number of red ball and black ball. If a ball is chosen at random, and it's found to be red, listen, what is the probability that it was chosen from box 2? Now see the question first, then only you will understand the intention of this Bayes theorem. It is saying that one ball was chosen at random and its color is already given. It was red, means the red ball has already occurred. A event has already occurred. A has already occurred. So this A represents this red ball in the example. So the ball chosen is already given, it is red. Not to worry, not to find any problem. It's already red. We have to go in the reverse way. We have to find that if the ball was chosen from box number 2. 3 boxes are there. We don't know from which box it was chosen. So here EK represents box 2. Means we require the probability of box 2 on A. Probability of box 2 on A. See, I will advise you. Formula is a different thing. How to apply this I am explaining. That's why focus. It's very easy for you. Everyone understood how to find the probability of R. This is the term. This is the final result. Now a simple question. This is first term representing box 1. Second term representing the selection from box 2. This is third term representing the selection from box 3. We require selection of box 2 probability. Simply take the second term because this represents selection from box 2 only. Means in numerator we will write 1/3 into 3/12 divided by, we are given that denominator will be of the event A. Event A means red ball, which we have already calculated to be 7/18. Or I will suggest you put this sum. Okay, put this sum, which will explain you actually 1/3 into 5/12 plus 1/3 into 3/12 plus 1/3 into 6/12. This explains that box 2 is favored by the second term, so we have taken it in a favorable outcome upon total number of outcomes. How to simplify? See, 1/3 is available. It's common in denominator. Cancelled out. We are left with 3/12 and addition of 5/12, 3/12 and 6/12. 14/12. Finally, it is 3/14. Check. That means whenever you are solving a question on Bayes theorem, simply total probability is the compulsory part of it. So you begin with the total probability and then you finish as in the form of Bayes theorem. Okay. So I hope with the help of this example, concept is understood to you. Still your doubts and comments.